Hello everyone, and welcome to my digital poster presentation for the Energy Simulation Summit in Brazil. My name is Sijmen Zwarts, I'm a PhD candidate at the University of Delft, and I'm working together with Hadi Hajibeki and Martin Nasur. Today I would like you to walk you through my poster, which you can see on the screen, which is about the evolution of the mechanical properties during the cyclic loading on the microscale. But first, let's dive a little bit deeper into the context of underground hydrogen storage. As we all know, hydrogen has the potential of being a completely carbon-free solution to our energy problem. We want to create hydrogen with a surplus of green energy sources and transform this green energy into hydrogen. Once we have this hydrogen, we can store it, and therefore we need large facilities because hydrogen itself needs around 25 times the volume if we compare it to methane in the same conditions. Therefore, we're looking underground to facilities such as depleted gas and oil reservoirs or even salt caverns. Once the hydrogen is stored, we can use it again when the demand exceeds what we can bring up with green energy sources. And therefore, we create, as you can see here as well in this graph, a sort of cyclic load on my reservoir. This can be either on the cap rock or this can be in my porous structure within my reservoir. And we know that this cyclic load has effect on the properties of my reservoir. This can either be on the permeability, affecting the reservoir properties, affecting the injection and extraction rate of the hydrogen, but this also has an effect on the mechanical properties. And we need to understand this, and we need to be able to predict this to ensure long-term stability, but also the efficiency and safety of our underground hydrogen storage facilities. On its own, cyclicity within rocks or in the context of rocks is not a new topic. We have some microscopic models, and with microscopic models I mean models which we have identified with experiments which describe the cyclic behavior of the rocks throughout time or throughout the cycles. But what we also know is that these models can vary significantly. This can either be in the parameters which you put in, this can also be within the components of your material model. Even two rocks which are very similar might differ very much between either the parameters or the model itself. Therefore, the idea behind this research is to zoom in a little bit and we zoom into the microscale. And what do I mean with the microscale? In a microscale is, as you can see here, is where we can identify each individual grains and the rock space and the void space around it. And if we zoom in the microscale, what we want is we try to understand the difference between the different microscopic models, and we try to understand where this mechanical behavior comes from. And with that, we try to create a constitutive law on the microstructure which can predict the mechanical evolution of the evolution of the mechanical properties throughout the different rocks. And in order to investigate this, we use something which is called the digital rock physics framework. In the digital rock physics framework, we usually do 4 steps. First, we have a real rock sample, and we scan it with high resolution imaging. This can either be micro CT, SEM, or whatever you like. Then we create a set of images, in which we can stack together and segment it to the different phases of interest. This can either be the rock material itself and the void space, or even going into different minerals. Once we have segmented this, we can merge all these images together and create a 3D digital twin of our lab real rock sample. We discretize this, and then we can run finite element simulations, even multiphysics, combining the flow and the mechanics or even chemical behavior to really predict what's going on the microscale. But of course, microscale itself is very hard to see in lab scale, and therefore we upscale our mechanical and even physical behavior again to the microscale, which is the same as the experimental scale. And from there, we try to validate what's going on within our simulations to the microscale. And for the modeling of the cyclic loads, we need to look at a couple of key characteristics of my cyclic loading. At first, we can distinguish 3 different phases. In the first cycles, we find a rapid increase of irreversible strain, as you can see in this graph. After that, we find a transition to a steady stage, in which we either have a small increase of irreversible strain per cycle, or we have a complete stabilization of the sample. The third stage is the acceleration stage, and this is connected to the fatigue or the complete failure of my rock. Another point is that there is no irreversible strain within the elastic zone, so if there is no plasticity occurring within my sample, I can load whatever I want. No matter how many cycles I will put in there, I don't find any irreversible strain accumulation. But before my plastic yield point, which you can see in this graph as well, and in between the elastic zone and the plastic yield point, I do find irreversible strain accumulation with a large number of cycles. And the fourth point is that the strain behavior is rate dependent. How fast I load or how fast I inject and extract my cycles has influence on the irreversible strain. In my model, I use very simple mechanics. I use an elastic part and a viscoplasticity part, specifically the Brezina model. I implement this on either, if it's available, the true microstructure, or I try to match the microstructure by matching a certain type of property of my microstructure, either the porosity, surface area, or whatever it is. I match my parameter of my material model on the creep test and on the monotonic stress strain curve. Then I extrapolate this to the cyclic circumstances, and what I can find is that if it matches, then my model is indeed correct. So let's look at the capabilities of my current model. At first and foremost, I can find that viscoplasticity indeed gives me the strain accumulation which I'm looking for. For each cycle, I have a little bit of an increase of irreversible strain. And if I implement the Drucker-Parker yield surface in my viscoplasticity, I can find the transition between the initial stage, in which the first cycles contribute a lot more, to the steady stage, in which the later cycles contribute less to the irreversible strain accumulation. And by changing the yield slope, I also find that the slope on which the steady state continues can be influenced. What is not implemented yet in this current model is the acceleration stage. This is something which is coming. Then we move on to point 2 and 3. What we find, indeed, if we load in the elastic zone, there is no strain accumulation. But before my yield point, which is shown here in the blue curve, I do find a little bit of strain accumulation, leading to what we call microstrains. What's interesting about this is that in microscale models, you need a creep law to model this, but we don't need this. We get this free from the microstructure, as before we find little points within my microstructure which have already gone into plasticity, but has not contributed that much that you can see it on the monotonic stress strain curve. This also results in less input parameters. And another fact, of course, with the viscoplasticity is that it's strain rate dependent, meaning that the load rate influences how much strain I accumulate each cycle. And to further investigate this, we want to dive deeper in the mineral composition of the rock, but also see the effect on the permeability. Another interesting thing which we will continue to look at is, if you look at this monotonic stress strain curve, you see that the rock will appear to become stiffer. This is what we call hardening, and we want to model that via contact also on the microscale. This is a quick run through to my poster. I hope you're interested. For any questions, please find my email address on the top, and thank you for listening.